Welcome to the Explainer. Today, we're looking at a totally fascinating piece of the puzzle behind modern artificial intelligence. We're going to explore exactly how AI learns from its environment. And we're not talking about patiently waiting for a game to end or some simulation to finally finish. We're talking about learning on the fly, step by step, without waiting at all. So if you've ever wondered how these agents figure out incredibly complex worlds so efficiently, you are absolutely in the right place. Now, I want you to just imagine for a second trying to learn a complex task, right? But you aren't allowed to realize you've made a mistake until you've already completed a 1,000-step journey. Imagine an AI model that literally has to wait 1,000 steps before it can update a single piece of information about its environment. This was actually the ultimate bottleneck of early AI. It required massive memory, and the episodes had to perfectly terminate before any real learning could actually happen. Okay, let's dive into this fundamental clash of two learning paradigms. On one side, we have Monte Carlo learning. Now, it works, sure, but man, is it sluggish. It basically waits around for the episode termination and that final return to come in. You get high variance, and it's just slow to update. But on the flip side, we have temporal difference, or TD learning. This approach updates after every single step using what we call one-step targets. It boasts dramatically lower variance, simply because it learns in real time. It doesn't wait for the end of those 1,000 steps, it starts adapting right on step one. So, how does this fit into the broader reinforcement learning problem? Well, to really appreciate why TD learning is such a huge breakthrough, we have to look at the unsolved gap it filled. We know those early methods like Monte Carlo were way too slow. Now, dynamic programming, it fixed the variance issue, but it required a perfectly known model of the environment. And if you don't have the literal rulebook of the universe you're operating in, it's pretty much useless. Which brings us to a crucial point, captured beautifully in this quote from our source material. This is the pivot on which all of modern RL turns. We aren't just talking about academic theory here. Understanding this single pivot point is the key to unlocking the foundations of modern deep reinforcement learning. Everything from deep Q networks to PPO, the algorithms running inside today's absolute most advanced AI models, they're built directly on top of the concepts we're breaking down right now. Let's look at the secret ingredient that makes this pivot possible: bootstrapping. Basically, this means using your current estimate to update your target. It's the core distinction between temporal difference and Monte Carlo. Think of it kind of like taking a road trip. Instead of waiting until you arrive at your final destination to figure out if you're on schedule, which, is the Monte Carlo way, you guess your final arrival time based on the very next mile marker. Sure, it introduces a tiny bit of bias because you're relying on an estimate, but the massive variance reduction you get, totally worth it. You're updating your values on the fly. And that is exactly where temporal difference comes to the rescue. Temporal difference learning steps in as this incredibly elegant mathematical bridge right between Monte Carlo and dynamic programming. It doesn't need a model of the environment, and it absolutely does not need complete episodes. From just a single transition, it forms a one-step target. Now, let's demystify some of this heavy AI jargon, right? Let's talk mechanics. TD error, which papers often call the update signal, is really just the bootstrapped residual. It's the mathematical difference between what you expected to happen and what actually just happened. Then there's TD0, which simply means we're updating after every single transition using only the next state. And GLIE? That stands for greedy in the limit with infinite exploration, which honestly is just a really fancy way of saying you need a correct schedule for exploring your environment so your AI eventually zeroes in on the optimal path. Which brings us to a real tale of two learners: Q learning versus SARSA. We have this fascinating rivalry in the AI space. Evolving directly out of the temporal difference updates we just discussed, we have two iconic algorithms that are essentially distinct personalities tackling the exact same problem. They might look super similar on paper, but the way they behave out in an environment couldn't be more different. Let's anthropomorphize these two a bit. First up, we have Q learning. This is our optimistic risk taker. It's an off-policy method that always assumes it's going to take the absolute best, greediest action moving forward, regardless of what the agent is actually exploring at that exact moment. Then we have SARSA. Think of SARSA as the cautious conservative. It's an on-policy method, meaning it calculates its updates using the action the agent actually takes next, exploration noise, and the whole shebang. Now here is perhaps the most surprising part of this whole comparison. The only difference between these two vastly different behavioral outcomes, the reckless optimist and the cautious conservative, is just one. Literally one single mathematical symbol in their code. Q-learning uses a max operator to blindly grab the highest possible future value, completely decoupling its target from its behavior. SARSA just leaves the max operator out. That one little symbol changes everything. Let's put them to the test, the classic cliff walking test. To really see these personalities in action, researchers use this classic setup where an agent needs to get from a start point to a goal, but walking right alongside the path is a steep cliff. And if the agent falls off that cliff, it gets hit with a massive -100 reward penalty. It's a super high-stakes environment where one wrong step ruins the whole run. And this brilliantly illustrates the real-world difference between our two algorithms. Step 1. Our risk-taking Q-learning agent figures out that the mathematically shortest, most optimal path is right along the edge of the cliff. It aggressively hugs that edge, but because it's still occasionally exploring randomly, it sometimes throws itself straight off the cliff. Step 2, our cautious SARSA agent knows it might slip due to that very same exploration noise, so it factors that risk right into its values and purposefully learns a safer path one step away from the edge. In life-or-death deployment scenarios, SARSA's conservative behavior can be absolutely crucial. But of course, we have to talk about common pitfalls and how to fix them. For any aspiring ML engineers watching, I gotta give you a quick warning. While these tabular temporal difference updates are literally just a few lines of Python code, they come with some pretty significant practical traps. Getting them to converge optimally means dodging some major pitfalls. So let's rapid fire through a few crucial architectural tips, because getting your hyperparameter schedules right is honestly the secret sauce. First, your initial Q values matter deeply. Optimistic initialization, like starting values at 0 for a negative reward task, forces the agent to explore. Second, your alpha schedule. Do not endlessly decay it. Pin your alpha somewhere between 0.05 and 0.3 to keep the learning active. Third, epsilon schedules for exploration. Start high at 1.0 and then steadily decay it down to 0.05. Finally, for non-terminating episodes, just treat your step caps as non-terminal and keep on bootstrapping. There's one specific pitfall we absolutely need to highlight, though: maximization bias. Remember that single max operator that makes Q-learning so optimistic? Well, when its Q-value estimates are noisy, taking the maximum of those noisy values actually causes it to wildly overestimate the true value of a state. It creates a massive bias. The standard industry fix for this, which was pioneered by Haddo von Hessel, is called double Q-learning. By simply splitting the learning across two separate Q tables, we completely eliminate that upward bias. Problem solved. So, how does all of this power modern AI? You might be wondering, why does mastering an 8-line tabular update even matter so much? Let's zoom out and connect the dots. If we really want to understand the massive, groundbreaking AI advancements we're seeing in 2026, we have to look at how these foundational concepts scale up. We start with Q-learning for small environments. For safety-critical tasks, we use SARSA. But look what happens when we hit high-dimensional states. We get DQN, which essentially just slaps a neural network onto our Q function. What about training those massive large language models? We use PPO or GRPO, which heavily rely on actor-critic methods, using a TD-style advantage. 90% of the reinforcement learning driving modern AI today, from ChatGPT's reward models to autonomous driving, is really just an elaboration of Q-learning or SARSA. Which brings us to the end of our explainer, and I want to leave you with a final thought to chew on. You now know that one single line of math dictates the entire behavioral foundation of an AI. The real question is, when you are designing your own systems, will your next AI model be an optimistic risk-taker, happily hugging the very edge of the cliff? Or will it be a cautious conservative, planning ahead for its own mistakes? The choice and the math is entirely up to you. Thanks so much for joining me.